Okay, thank you. Yeah, so I'll be talking, this is a very basic tutorial talk on quantum computation and simulation. In fact, the first part of the talk, most of you probably knows, I'll be just talking about qubits, gates and stuff. There are a few demonstrations that I'll be showing you. That's why I screen shared. So let's just start with it. Yeah. So, as I said, probably most of you know what qubits are at this point. Qubits are quantum analogous to bits, but in reality, these are representations of two-level systems that you can find in nature. A two-level system has, as it says, two levels of energies, one ground state and one excited state. A particle can be in one of these two states, but we don't know that before we measure the state. So for a quantum particle, it can also be in between. We call this a superposition. It can also be in a superposition of the ground state and an excited state. The mathematical representation of a qubit is a vector. For one single qubit is a 2 cross 1 vector written as 1 0 and 0 1. We traditionally represent the ground state as 1 0 or excited state at 0 1. The only condition that a qubit can have is this representation can have is the particle has to be somewhere. So in this block sphere representation, as you know, the qubit can be anywhere on the surface of the sphere if it's a pure state, but it has to be somewhere on the surface because of probability. So the probability is probability constrains it to be somewhere on the state, and that is why the coefficients of zeros and one, the square of them has to be summed to 1. So in the quantum domain, the particle can be in a superposition, but we don't know that until we measure. We live in the classical world. So until we measure the state of the qubit, we don't know where it is, and this process is measurement. And we can also write multiple qubits in this notation. What we need to do mathematically is to make a tensor product of two state vectors. If the state vectors are in both in ground state, then it's a tensor product between 1 0 and 1 0, and you will get a 4 cross 1 state vector. So for a 2-qubit system is on a 4-dimensional space. Again, the probability constant is still there. Yeah, so 2-qubit systems are in 4-dimensional space. A 3-qubit system is in a 8-dimensional space. Subsequently, an n-qubit system is a vector in a 2 to the power n-dimensional space. Now, think about representing a data set that has, let's say, 256 elements in it. In order to represent it on a classical system, you need 256 bits of bases, let's say. But on a quantum system, all you need is 8 qubits to represent a state. So this gives opportunity to invest in quantum computing, because this gives us an exponential advantage in space. Sorry, with respect to the classical domain. Now, bridging on to my previous analogy, representing the data is not always enough, right? So when we represent the data, we also manipulate. We also need to manipulate the data. So on quantum domains, manipulating a qubit is a gate. The name gate actually comes from mimicking classical terminology. And mathematically, how do we manipulate a 2 cross 1 column vector? We apply a 2 cross 2 matrix on it. If you think about the dimensions, it makes sense, because 2 cross 1 column vector, we want to take a 2 cross 1 column vector to another 2 cross 1 column vector. And in order to do that, we do a 2 cross 2 matrix multiplication on it. In order for the matrix to be quantum, it has to follow unitarity and hermissivity. And these are a few common gates. These are single qubit gates, which means that you can act on a single qubit. There are Hadamard, Pauli gates, phase gates, and T gates. The Hadamard gate, it's an example how it takes this one qubit from one state to another. The state you see here is the ground state 1, 0, and I'm taking it to a equal superposition of the ground state and the first excited state. And the way to do it is to act a Hadamard gate on it. In reality, in an actual quantum device, this operation is done with physical systems, lasers or microwave pulses, depending on which system you are looking into. But this is how we mathematically express it. There is one more type of operations that we need to know in order to fully understand or replicate quantum systems. That is a 2-qubit gate. So this is an example of a 2-qubit gate. That 2-qubit gate, and this particular 2-qubit gate is controlled not. So here you see 2 qubits, one is control and the other is target, and we start at different states, as in the truth table. As you can see from the truth table, we start at different state and we end at different states in some cases. For the first example, both the qubits starts in the ground state and they end up in the ground state. For the third example, on the contrary, we start at the first qubit on the excited state and the second qubit on the ground state, and we end up with both qubits on the excited state. This happens because we are taking the first qubit as a control and the second qubit as a target, and we are defining the action of the gate likewise. So the rule of this transformation is, if the first qubit is in excited state, we make a change, and the change here is not. Think about classical NOT gates. So what does it do? If it's in state 0, it turns it into 1, and if it is state 1, it turns it into 0. There are other examples of similar to qubit gates like control Z or control phase. What it does is you take the single qubit operation of Z gate and you act the control operation on it. This is the matrix that does this operation, and as I said, in reality, in an actual quantum computer, this will be done with maybe microwave pulses with qubits in resonance. And with that, we are at a place to build our first quantum circuit. This is a celebrated quantum circuit. This builds the Bell state, the maximally entangled state. We will go slow one by one. So we start at both the qubits at the ground state, as you can see from psi 0. This is at 0, 0. Then we act the Hadamard on the first qubit and we take the state of the first qubit to a equal superposition of 0 and 1. But we don't touch the second qubit at this point, and there is no operation on the second qubit. We are still able to write the states of both the qubits separately. In this case, the first qubit is in plus state or the equal superposition state, and the second qubit is still in ground state. But then we do this controlled not operation from the first qubit to the second qubit, that is to say, the first qubit using the first qubit as control. And what happens then? If the first qubit is in 0 state, nothing happens. If the second qubit is in if the first qubit is in 1 state, then the state of the second qubit changes to 1. So by doing this operation, we have entangled the qubit. What does it mean? If you look at state psi 2, there is no way you will be able to write one qubit as a separate system. This is what entanglement means. You will not be able to write the two systems separately. Now, this is also an equal superposition of these two states, 0, 0 and 1, 1. And how do we know that we have built this state? We measure it. We measure it a few times. I will show you measuring just once doesn't work. You have to measure it a few times. The more you measure, the better. And in the end, if everything is perfect, you will get, if you are measuring 1,000 times, you will get 500 times 0, 0 and 500 times 1, 1, meaning that you have created a state that has 0, 0 and 1, 1 in equal probability, and that's why the state is like this. So yeah, we are going into the demonstrations now. I think you can see the VS Code. Yeah. So this is a IBM Qiskit demonstration. This is not real quantum device. I will not be showing real quantum simulations. So here are the imports. We don't care about the imports or the version right now. What we care about is to build this circuit using Qiskit. So this is the circuit we are going to build. I have built it beforehand to save time. So you have a definition of a quantum circuit. I have written 2 and 2. The first 2 means 2 qubits, 2 resistors, and the second 2 means 2 classical resistors for measurement. And first I have applied a Hadamard gate. In Qiskit, you import gates and then you just do qc.h. 0 means which qubit you want to apply the gate on, and here I have the C0 gate. The C0 is just Cx in Qiskit, and you define the controls in the first position, which is 0, and the target on the second position, and then you measure. You define it. Remember, there are 2 and 2, and you define which resistor measures into which resistors. In this case, 0 measures at 0 and 1 measures at 1. So this is my circuit. This is Qiskit's own function to draw. So I am drawing the circuit here, and this is exactly what we have drawn by hand. And yeah, now, sorry, like I said, if we have built the circuit, how do we know that we have built the circuit? In order to do that, we run the circuits through different backends. Backend is actually what it says. It's a backend. The front end is your computer, your VS Code, whatever. And backend is the device that your circuit will be run on. In principality, this should be the actual quantum devices of IBM. But those are noisy and expensive. I'll tell you in a second. So we run them through different simulators. I have been talking about state vectors or vectors in my presentation. So the first one we will see is how we represent in that form. And way to do it is to define your backend as state vector, and then you run it. It's taking a little bit more time than it should. I don't know why. Yeah, it's there. So this is exactly the form that I had on the presentation for well state, 1 over root 2, 0, 0 plus 1, 1. Well, this is root 2 by root 2, which is basically 1 over root 2. We can also see the state vector, the actual state vector, what we are getting. And here you see this is the vector form. Well, the transpose of this is the vector form. For visualization purposes, I have written it as a row vector, but in actuality, this should be a transpose there. There are other simulators. I'll just show you for this demonstration. I'll just show you what other simulators you can have, and we will know what those simulators are in the process of this presentation. So there is something called a MPS simulator. MPS is matrix product states. Those are very useful, as we will see later. And see, this produces the same state. But if you notice here the representation is not the same anymore. Here we had a 4 cross 1 array, but now 4 cross 1 vector. Now we have a bunch of different of arrays of different sizes. In fact, it tells you what the object is Pythonically. It's a tuple with 2 elements in it. Let's not care about that right now. There is another simulator called stabilizer simulator. We will briefly touch upon it today. But if you run it through the stabilizer simulator backend, you see this is something very interesting. Instead of having any kind of state, any kind of vector, we now have 2 strings, two objects. One is plus xx and one is plus zz. Those of you who are from physics background, you know these are Pauli operations. Actually, we also have these as gates on the slides, but this is two Pauli X operators with a plus sign in front of them, and these are two Pauli Z operators with a plus sign in front of them. Let's ignore it for now, but the point of showing it to you right now is this is different object than what we had when we used the state vector simulator. Okay. Finally, now we are at a space when we can actually see what happens if we run the circuit through the quantum device. But like I said, quantum computers are expensive and noisy, so we are not going to do that. Instead, we will send it through the measurement simulator. So if you want to simulate your algorithm, if you want to know how your algorithm will perform on an actual device, this is the simulator you want to use, the measurement simulator. So now we have incorporated the measures. Measure all is basically an instruction that tells Qiskit to measure the circuit. These are measurement gates, and this is my classical register where I will read the outcomes. Okay, so this is still the Bell circuit, and now I am going to run the circuit, but with short equal to 1. The short equal to 1 means I'm just going to measure once. This will give me an error because I have printed different stuffs. Let's comment out the print. Yeah. So you see now I have the measurement outcome, and it tells me that the measurement outcome is just 0, 0 once. I will do that again. Now it's 1, 1. Again 0, 0. Again 1, 1. So I don't know before. I don't know which state my system is in, 0, 0 or 1, 1 before I measure. But after I measure, I know. That's what I wanted to show you. Now, if I increase the shots, what Qiskit will do, it will do this process internally. It will measure the circuit 100 times and give me back the output of how many of these 100 times it got 0, 0 and how many of these 100 times it got 1, 1. And now I have the counts. It got 1, 1 51 times and 0, 0 49 times. Now I can print the probabilities. So probability of this time, this is very rare. It actually got it 50 and 50. So the probability is 0.5 and 0.5. I didn't thought that this will happen, but anyway, if I increase it, now this is more close to what you will actually get. The more you increase, the chances of you getting the actual probability 0.5 and 0.5 increases. This is a visualization technique. You can plot the counts in terms of bar plots, and you see that in our outcome we have 0, 0 with almost 4.9 probability and 1, 1 with almost 0.5 probability. It's very rare that you will actually get 0.5 and 0.5. You might get it. We just got it. But this has nothing to do with noise. At this point, this has nothing to do with noise. This is just probability being probability. Okay, but as I have said like 3 times now, real devices are noisy. So we need to know how much that noise can impact our algorithm outcomes and if we can do something about it, right? So IBM provides a way to not spend your money or time on the real backends and instead use the fake backends as a good approximations. So this is one device that at least was online, IBM Brisbane, a year back. I don't know if it's online now, but I have imported that. So I'm importing IBM Brisbane, the fake version of it, where they have hard coded the noises in the actual devices or a very good approximation of what the noises are in the actual devices. And I am running the same circuit on that fake backend with 1,000 slots. Now you see something interesting. In the previous plot that we had, we didn't have the two states 1, 0 and 0, 1. We just had 0, 0 and 1, 1. But now that's not the case anymore. we have 1 0 and 0 1 with very small number of counts, very small probability, but we do have them. This is the impact of noise. The noise present in the IBM, or not only IBM, any real quantum device will mess up with your circuit, and this is just a result that shows you how. So okay, this is the first demonstration. We will go back to the presentation now. I'm keeping the questions for the end. So yeah, this I have probably already answered this question in brief, but again, why do we simulate? It's not only because quantum computers are noisy and expensive. Well, those are the major reasons. You can see from the first picture here that there is at least 30 to 33% error in a quantum device, in a quantum QPU backend. In this case, IBM Q, some device of IBM Q. And also this is very costly IonQ device. In order to access one of the IonQ devices, you might have to spend 750 for 10,000 sorts, and 10,000 sorts is just one iteration of your algorithm. It's not even the whole algorithm, let alone the paper. So development of algorithm requires something that helps you simulate the circuits. But the most important of this list is that classical computation is not hopeless. In some cases, classical computation is almost as good as quantum computation, and I'm not talking about classical problems. I'm talking about problems that are solvable with a quantum computer or models the quantum systems. You can simulate them classically if they follow some rules. So knowing those rules or defining that boundary is also as, if not more, important. So here today we will be talking about three different classical simulation methods. One we have already done, a state vector simulator. We'll keep referencing to it because this is the exact method of simulating a quantum state. It works for almost everything, but it's very expensive. And this time I do not mean in money terms. This time I just mean that it's expensive. Tensor network popular now, I will say. So tensor network simulation methods is very popular, and but they are good if your circuit has structures in it. Here I have an example. MPS is just an example, and this is the example we'll cover today. So this is the example. Actually, we did this in SOA, so this is also something emotional about it. But anyway, so this is a approximated QFT simulation with MPS, and you can see that we have gone to 50 qubits. 50 qubits QFT with state vector is not possible. It's a 2 to the power 50 dimensional array that you are working with, and I think the best the best supercomputer in the world can simulate up to 52 or 53 qubits. So your desktop will not be able to do it, and this is done in my own laptop, not even a workstation or anything. There is also a method called, I showed you a glimpse of it, stabilizer or tableau method. And this is very fast if your circuits follow some rules. In this case, the rule is Clifford. So if your gate, if all your gates are Clifford gates, I will tell you what Clifford gates are later. Then this formulation is brilliant. It is exact. It's not approximated. MPS is approximated, but Tableau is exact. This gives you exact results, and you can scale up to 1000 qubits, as you can see. So this is Ising model. We have transformed Ising model under a Clifford circuit with 1000 qubits, and it was done within 100 seconds. Okay. So for this part, we'll be talking about tensor networks. Very brief introduction of tensors. Tensors are generalized matrices. Matrices are matrices are two-dimensional. Tensors increases or decreases the dimension. A scalar is order 0 tensor. A vector is order 1 tensor. Matrix is order 2. You can define higher order tensors as well. How does that relate to our course? Well, we were defining quantum states and quantum gates in terms of matrices and vectors. So there is a one-to-one correlation here. So we can represent a single qubit in a vector. If it's a vector, then it's a order 1 tensor. A single qubit quantum gate is a 2 cross 2 matrix. So this is a order 2 tensor with 2 legs. But for a 2 qubit gates, it's a 4 cross 4 matrix. So it's a order 2 tensor, yes, but with 4 dimensions. So this is how do we do that? We do a Python reshape. The reshape is a Python reshape. We go from 4 cross 4 to 2 cross 2 cross 2 and 2. So 16 elements reshaped into 16 elements, but the ordering is different. Okay. Now, if we have a way to represent a single qubit and a 2 qubit gate, that is universal, right? So universal gate set has only single qubit gates and 2 qubit gates. So if we can represent the single qubit and 2 qubit gates in terms of this representation, we can represent any quantum circuit in this representation. So this is a randomly generated quantum circuit, and this is the tensor network. The composition in it, I recommend this library. If we have time, we can go into it, but we don't have time right now. So we will not go into the library, but know that there is a library that will do this for you. MPS, yes. MPSs are a particular version of tensor network. It's not the only tensor network you can define, but it's one of the mostly used one, and it represents a quantum state in another form. So in this representation, we have the basis and the coefficients. So instead of storing the coefficients into a n cross 1 dimensional array, we will be storing them in small matrices. So these U's are matrices, and this product is basically a product of matrices, and hence the name matrix product state. This is a pictorial representation. So psi is a tensor. This is all tensors. So psi is a tensor with 3 legs. This is a 3 qubit state with 8 elements. So we will decompose this state into 3 small matrices with smaller dimensions. So this is 3-legged tensor with 8 dimensions, but this is like 3 tensors with dimensions 2, 4, and 2. So this is how we do it. We have an array of 8 elements. We reshape it into a matrix. Then we do singular value decomposition in it. This is a neat trick that will help us represent anything, not anything, represent a portion of a few quantum states very efficiently. So we do a singular value decomposition, and the first matrix is 2 cross 2 dimensional. We separate it and we build another matrix that is also 2 cross 4. We again reshape it into 4 cross 2 so that we can separate out another 2 cross 4 matrix. And finally, we have a 2 cross 2 matrix left. So instead of a 8 cross 1 dimensional array, now we have U, which is 2 cross 2. We have U1, which is 2 cross 4, and we have M2, which is again 2 cross 2. I'll show it to you, so it will be clearer when we do the demonstration. Okay, but if you noticed that this is 2 cross 2 and this is 2 cross 2, but this is not. This is 2 cross 4. So this happens when you have higher dimensions, right? So this is an artifact that comes from the fact that where are you cutting the circuit? We will come to it in a moment. So here we have these across these junctions, the dimensions grow. So this is a 2 leg, this is a leg with dimension 2, but this is a leg with dimension 4, and this is a leg with dimension 8, and then it reduces. So here we have 1, 2, 3, 4, 5, 6 legs. So it was supposed to be 2 to the power 6 dimensional tensor, or a tensor with 6 legs and each leg being 2 to the power 6. Instead of that, we have 8, which is 2 to the power 3. So there is already a reduction, not much, but already a reduction. But we can also control this bond dimension. So this thing is called bond dimension, and it grows as you increase the number of elements in your matrix product state. But we can also approximately control the bond dimension. The way to do it, as I said, we are doing singular value decomposition. We can truncate the singular values at any point, and through truncation, we can remove this 8, we can reduce this 8 to a 4. That will screw up our state, that will make our state less representative of psi in general. We will also see it in how does that happen in actuality. But for now, just trust me. And this is the physical reason behind it. So the bond dimension grows because this is a representation of what happens if you cut it at these points. So if you cut at between U0 and U1, you have one system which is basically less important. But if you cut it here, then you have 3 systems and 3 systems each. So the entanglement between these 2 systems will be high, and there is a correlation between these two. Now this is 2 to the power n by 2. This is not what will happen in every case. For a product state, this will not be 8. This will be 1 throughout, because there is no entanglement. So the point that I'm trying to make is, if your entanglement, if your state is highly entangled or genuinely entangled between multiple parties, then the bond dimension grows, and using singular values decomposition and truncation to cut the relevant features of your state doesn't work anymore. So MPSs are great. Use MPSs if your state follows a area law of entanglement, and just keep this in mind for the purpose of this talk. Might be useful for some of you in later. Okay, this slide is here to show you that MPSs are not the only tensor network method. There are lots of tensor network methods in actuality, and this is one of the very complicated circuit that doesn't follow area law. This is the first quantum supremacy that Google advised in 2019, I think. And they predicted at that time that classical simulation will take 1 billion years to reach the level of accuracy that they got for this circuit, for this particular circuit. This is the tensor network representation of this circuit using this library, and in reality the classical simulation on a HPC, but it took only 28 days. So, and that was in 2021. By now I think they have reduced it to 1 or 2 days for this particular circuit. So, but this is not done with MPSs. This is done with, I think, hyper optimized tensor network contractions. It's another method. Okay, so with that we go into demonstrations again. Yeah, this time we will be doing MPSs with the library QIMP, and first we will see the truncation in effect. So I have generated a random matrix. You have a random matrix. You do the singular values, just focus on the matrices. So these are the singular values that you have in order of importance, and also the first one is greater than the second one, and likewise. So by truncation I mean manually ignoring this value, and if we do that, this is 0, and I'm just building back the matrix. This is also a random matrix, and we will see what the distance between the two matrices are, and it's close to 0.006, which is very less. So the point of this, showing this to you, is you can do singular value decomposition and truncation, and for some matrices and some limit of truncations, it will work splendidly. It will get you a very close approximation of what you want to simulate. With that, now we will see how to build an MPS, first manually and then with QIM. This is a 1 qubit state, and this is how we represent it with QIM. The point of showing this is there is no reshape. There is just it was already a 2x1 matrix, right? So there is no reshape. There is nothing. It's happening. You just pass it through the tensor network, and it builds the tensor network for you. But if we have more than 1 qubit, then we have a 8x1 vector.
Hello, Dr.
Sorry.
Vanan, can you make your
Yeah.
font size a little bigger because it's very difficult to visualize your things. So make it little bigger, please. Yeah. Correct. Thank
This
you.
one
Thank you so
bigger,
much.
I can. Is it bigger now? I guess.
Yes, correct. Little
Yeah.
more.
Okay.
Oh, thank you.
I can also zoom in a little bit for you. This is fine. Okay. So yeah, if you take a one single qubit state, then you don't need to do anything. That is what I was saying. But if you take a three qubit state, then the first print here. Let's comment out the second print so that it's easier to understand. Sorry. Yeah. So you have a 8 cross 1 dimensional array here, which is fine, but we cannot directly pass it through the tensor network. Let's try. Won't happen if I don't do that. So this is a 8 cross 1 dimensional array. I pass it, I get an error because the tensor network doesn't understand the 8 cross 1 array as an object. But if we do the, see, this is just numpy reshape. This is simple Python reshape into 2 cross 2 cross 2. And now we have three arrays, sorry, two arrays with 2 cross 2 elements. And now this will be, yeah, this is just fine. So this is a tensor with three legs. Each legs has dimension 2. Now we will build an MPS with it. This is just the process that I have already showed you. First we do a SVD on the 2 cross 4 matrix and separate out the first tensor. The remainder is a 2 cross 4 matrix. We do a reshape, turn it into 4 cross 2, and then we do another SVD, and then we do finally a reshape of 2 cross 1. So this is, sorry, this is the second one before doing the third thing, and this is the third one, which was in this case, since this is just a 3 qubit state, this was already in this shape, so we didn't need to do any SVD anymore. So the shapes of these matrices are exactly we said, and if we pass it through the tensor network, this is the MPS that we had. So we have three tensors, the first one with two legs, the second one with three legs, and the third one with two legs again. Okay, this was the original tensor. Now you don't have to do these SVDs by hand. You can just import QTN is quim.tensor. So if you can just import matrix product state and you can pass the psi to it, and you can just build the tensor, the matrix product state likewise. Yeah, so I told you that bond dimensions grow with tensors, and this is a 12 qubit state, and I have kept the bond dimension as 10,000. I didn't need to do that. What is 2 to the power 12? What is 2 to the power 6 really? It's 64. So 64 should be enough. See, so the last part of these arrays are bond dimension. The first one and the last one is omitted because it's just one. But if you see in between, it increases 4 to 8 to 16 to 34, and then 64 because it's 2 to the power n by 2. This is where I do not truncate, but I can truncate. Before that, I just want you to show the fidelity of the state. The fidelity of the state is 1, and this means that I have accurately approximated the original state that I was given. I can cut the bond dimension now, and I decide to cut it at 5. See, now the bond dimensions doesn't grow because through the process of the SVDs that I haven't done it. Quim has done it for me, but throughout the process, it has cut the first 5 singular values. Important thing to notice, the first one didn't have that many singular values. It just had 4, so there is no truncation here or here, 4 and 2. So this, since I have taken a random quantum state, a random array as a quantum state, this state is very entangled. So this will be a very low fidelity, and yes, in this case it's just 0.6 fidelity. So this is not a great approximation. But sometimes you can get, for some states, you can get a better approximations of 0.9, 0.91, 0.92, and those are usually fine. And for the states that already follows area law, by area law, I mean the bond dimension doesn't grow. Like an example is a product state. In this case, I have taken 0, 1 times. Okay, I'll show you what state this is. Binary. Yeah, so this is the state 0, 1, 0, 1, 0, 1, 0, 1, and I have passed it through the same process, and this gives you the bond dimensions of the state. So the bond dimensions I am truncating at chi, and each line is basically where it is truncated, it's 1, and the fidelity is 1. It's truncated at 2, the fidelity is still 1. Why is that? Because the actual state had bond dimension 1. It didn't increase. Even if you increased the number of particles in it, it didn't increase. So you can also build MPSs of known states. This is just a product state 0, 0 of 2 qubits. See, there is no connection here. So you can also build a Bell state. The way to do it, it's very easy. The gates are also encoded is in Quim as Hadamard and Quim control not. So you just import those and you run this. This is the exact Bell state that we got from Qiskit, and this is the tensor network approximation of it, the MPS approximation of it. Now I will show you why do we do this. So I have created a 100 qubit quantum state, computational basis state, and I have applied a Hadamard gate on it. So P is basically a 100 qubit quantum state, and Q is a 100 qubit quantum state with the same, it's the same state with a Hadamard on it. So if I do this, I'll be calculating the expectation value of Hadamard with respect to the state. And it calculates. That's what I want to show. This is a 0 state, all 0 state, and Hadamard it takes you to 0 plus 1 equal superposition on that particular qubit value. This is the particular qubit value. So it actually gives you the exact result. So we just did an expectation value calculation with 1,000 qubits. So this is the power of tensor network simulation with tensor network. I would like to ask, how much time do I have? Professor Chaturvedi?
Sorry, my phone was on.
Srivastav, sorry.
Yeah. You have 8 minutes for the talk, then you'll have 10 minutes of discussion session.
Okay. So if I have 8 minutes for the talk, I'll skip demonstration 3 and go into the third simulation technique directly. And this is something that I am really excited to show you, because this is coded by us, and the library is coded by me and my group here at Exeter. It's not my group, but anyway. So this is efficient and exact simulations with tableau representations of Pauli sums. So this is already physics heavy. Again, this is a representation that Gottesman provided long back, but this is a representation not in the state vector space anymore. So those of you who are from the physics background, it's not Heisenberg picture, but think Heisenberg picture. I would further emphasize that this is not Heisenberg picture, but this is similar to, you can think of in that line. So what happens in Heisenberg picture? In Heisenberg picture, you dynamically evaluate the operators. Here, we will manipulate the operators directly with an efficient representation. I'll now explain what efficient representation means. So these are the Pauli gates in qubit dimensions. We all know that. And it requires, the single qubit Pauli operations requires 4 elements to represent a gate. Whereas they also form a basis, and you can represent them this way. So identity, you can define 2 exponents, x exponent and z exponent. You can define identity as 0 and 0 because it has neither x nor z. Pauli x, since it's in the name. So Pauli x is x exponent 1, z exponent 0. Pauli z is x exponent 0 and z exponent 1. Pauli y is approximately exit because it's a phase correct, I mean up to phase basically. So this is identity exit or minus identity exit. But for the purpose of these representations, think that this is up to phase exit. So this has x exponent 1 and z exponent 1. So in the Hilbert space, we needed 4 elements to represent all of these gates, even identity. But in this representation, we just need 2 elements. So this is a efficient mapping of our popular Pauli gates. And since we can define Pauli gates in this representation, anything that maps a Pauli to a Pauli is also efficient in this decomposition. How is that? Take this Hamiltonian for example. Sorry, this Hamiltonian is it's a very commonly, I mean, not this particular Hamiltonian, but this is a form that most of the physical Hamiltonians have. So these are sums of Pauli terms, and we have a representation of this Pauli sum. We call it Pauli sum because it's a sum of Paulis. So this is the representation that you can write this in, and only instead of 2 to the power 2n elements, you only need 2 mn elements. M is the number of terms in your Pauli sum. So if you want to take this Pauli sum to another Pauli sum of the same dimension, you need a 2n cross 2n matrix. So instead of 2 to the power 2n elements to represent a gate or a circuit, you just need 2n squared matrices, which is a exponential reduction in space. Okay. The demonstration for this will be this one, circuit simulation with SympleQ. SympleQ is the tool that we are building. Like I said, it takes Pauli to a Pauli. You can, the common gates we have encoded for you, so you can just directly pull them. This is how, this is an example of how you can write the Pauli sum. So in this case, I have taken a very simple Pauli sum with the z on the first qubit, nothing on the second qubit in the first string. For the second string, we have x on the first qubit, nothing on the second qubit, and for the third one, I have 0, 0, and I have coefficients here. So 1.5 and minus 1.2. No phases for this example, but you can also incorporate phases. So this builds the Pauli sum for you in the representation that I just showed you. You can inspect what is there. The tableau is the representation. It's the actual representation, but it will also give you the coefficients on the left and phases on the right. In this case, there is no phase. So you can all check those things by hand. Dimension is something that is very special to this library. I will come to it. For this particular example, see, dimensions are all 2, means these are all qubits. So we can act a Clifford circuit on the Pauli sum. We can build the circuit from the gates and where we want to apply those gates. And here we have a circuit on 3 qubits. You just act on it. You just act it on the Pauli sum, and this is how you have taken from this tableau to this tableau. We can do 1000 qubit simulations right now, maybe. Let's see. I have defined a chain circuit. So I have 1,000 positions, 1,000 qubits. This is the qubit, and depth of my circuit will be 10 here. So this is the chain circuit that I'm doing. You see, I have 14,000 gates in my circuit and 1,000 qubits in my circuit. This is just for visualization. This is the chain that I'm applying. You see, there is the some combinations of Hadamard and S gates, and then CX, CX, CX. Notice that there is no T gate. T gate is not a Clifford, and T gate doesn't work in this representation. So which will take 1.5 seconds, so we can do that. It took 2 seconds, and you have done a simulation with 14,000 gates and 1,000 qubits. So with this library, those of you who are interested, you can also do beyond qubit simulations. You can do qubit simulations. So here you change the dimensions and you will be able to define qubits. See, there are x2 in this tableau. 2 means the exponent of x is 2. So, and remember, in this case, we are not using the Paulis that were on the slide. These are generalized Paulis or Weil operators, and x to the power 2 is not identity anymore. X to the power 3 is. So, this is x square, which is a non-trivial Pauli operation in Q-trig dimension. We have hard-coded physical models for you. This is just an example. There are a bunch of chemistry Hamiltonians, bunch of fermionic models as well. So this is the Ising chain with 100 spins, and I will run the Clifford chain circuit for you for this chain. And you see, it took 0.2 seconds to run a 100 qubit Ising chain simulation. And I have made this plot for you. Coded, we can do that. It won't take much time, but let's not do it right now. So here we have done a 500 up to 500 qubit simulations, and it's just took less than a second or 10 seconds approximately. So the point I want to make is that with this kind of, so the restriction here is Clifford's. If you have a T-gate, you can't do it. If it's Shor's algorithm, you cannot do it. If it's QFT, you cannot do it. Anything that has a T-gate in it, you cannot simulate that circuit with SympleQ or in these representations. But that doesn't prevent you to do a lot of things, as I will show you. These are two results from last year, this year actually. So one of these does different model simulations with our framework, and there is Heisenberg. TFI is the Ising model with disorder. So you see, with the help of these simulations, we have done up to 32 qubits, where with a 64 GB computer, where the exact simulations would have taken us only to I think 24 on the same computer. Here you would want to look at, sorry, here you would, this was a bad idea. Here you would want to look at the black line. The black line is the exact simulations, and you see we have done up to 10 to the power 2. This is symmetry finding, but we have done 100 qubit simulations with random, even random Hamiltonians. So these are a few where these kind of simulations work. You can do error tracking, error corrections are all stabilizer states, so you can efficiently do that. You can do randomized benchmarking of quantum computer, and you can obviously do symmetry finding or Hamiltonian reductions like we did. And well, this is the last slide of the talk, which says that why simulators are not enough. It depends on what model you are using. State vector simulators are exact, like I said, but it will not give you, it will not help you get beyond, let's say, well, on your particular computer, if it's 16 GB like mine, it will not let you do simulations more than 14 or 15 qubits. But use it when you have a small number of qubits in your algorithm. Tensor network, particularly MPSs, works with low entanglement if your algorithm doesn't let the entanglement of your initial state grow. And if the initial state entanglement is also low, then use it, use MPS. There are other networks for structured, explore and use them. If you have all Cliffords, come to me, I'll help you do it with SympleQ. And with that, thank you. I'm open for questions.
Okay, thank you very much. Hello, thank you very much, Dr. Banerjee. Okay, now the session is open for discussion. So people who want to ask questions can unmute and ask questions.
I have two questions. Allow me to ask.
Yep.
So first of all, thank you for a very interesting and informative talk. First question is on slide number 18. You have shown representation of vectors in the form of small matrices. question. Do we have automatic process to use this transformation efficiently by using input state as a vector?
Yes, so that's what I have shown you here. It means, I mean, it depends what do you mean by efficient. Some states will not be efficient by the laws of physics. So, like in this case, in the example that I had shown you, let me go back. Yeah, so this was a randomly generated vector. If I print dot shape, I think, to print. Yeah, see, so this is a, well, this is a 2 cross 2 cross 2 cross 2 cross 2 thing, but this is basically a 2 to the power 12 cross 1 vector. So you input that to the code here. So this is the psi, and this is the matrix product state. I was talking about truncation. You put the bond dimension is that parameter where you want to truncate. If you do not truncate, since this is a 12 qubit gate, it will be 2 to the power 6. So if you do not truncate, this is the exact decomposition and the fidelity will be 1. But if you do truncate, depend on where you truncate. Let's say let's truncate at 16. So see, few of those now just restricted to 16 and the fidelity will decrease. So depends on what you mean by efficient. There are some states for those where these will not increase, then you have an efficient decomposition.
Yeah, allow me to refine my question, because in quantum optics or in bosonic fields, we have, for example, not discrete variables, but continuous variables. So in that case, we have to use some quantization and then try to find out the effective algorithm to transform that continuous variable state into small matrices. So that was my question. Yeah. So I think
in that case, I think instead of using the Quim QTN method, you can directly use the SVD process that I was describing and the reshape and SVD thingy. So actually, you know what, these tutorial these are available at my GitHub repo. So feel free to.
Thank you. My final question.
Yeah.
My final question, could you name the packages required to replicate codes shown to us?
Yeah, so this is the repo. You can still see the screen, right? I think so, yes. So this is the repo, this is public. In the README, I have linked everything. Qiskit is there, SympleQ is also there. This is the tensor network. So this is the tensor network repo. This is the this is the repository for Clifford simulation. This is the tensor network. Sorry, this thing is irritating me. Yeah, this is the tensor network simulation library, and Qiskit is Qiskit. Everybody knows Qiskit. So
thank you.
Seems like no other question. Go ahead. There's one question. Please.
Let's say I have a system which has 100 qubits. So this will can simulate up to a problem that has 2 to the power 100 Hilbert space. So I have a system.
2 to the power 100. Sorry, 2 to the power 100.
Means we can simulate a problem. The system, this problem is for a system which has 2 to the power 100 Hilbert space, right?
Okay.
So let's say I know a Hamiltonian that can be represented in 2 to the power 100 dimensional Hilbert space. So how can I write this big matrix in the first case so that we can simulate in the quantum computer? So means how can we
Yeah, you
write?
can't. You can't write a to the power 100. This was the point of this representation technique. You cannot write a 2 to the power 100 dimensional matrix with the computers that we have anywhere in the in Earth, let's say. So, but if it is a Clifford Hamiltonian, if it's a Pauli Hamiltonian, not Clifford, if it's a Pauli Hamiltonian, that is to say, if all the elements of your Hamiltonian is Pauli, then you can write it as a how many terms there are. Let's say there are 100 terms, so 100 times 200 matrix. That you can write.
I see. So we have to figure out a way so that we can write our problem in a Pauli form.
I mean, yeah, you need to figure out a way. But before that, there is another step. You need to figure out if it is possible to write your particular problem in terms of Pauli Hamiltonian.
Or
If
is there
you
any
can,
other way? Or is there
I
any,
mean, what did you say? What is the?
is there any other way we can do this problem? Because this bothers me actually. So let's say we have this much big system and we can't use it.
अप्लाई किए थे वो आ गया ना
I can't. I couldn't hear the last thing that you said. Sorry.
अरे हम वो ठीक है वो डेट थोड़ा पता कर सकते हो कब आया था वो हमने जो लोग बिल सबमिट किया था ना
Can you please mute? Hello, there's a conversation going on. Please mute yourself. There's a discussion continuing. Yeah, please continue. We have to finish the discussion quickly, so please brief, make it brief. Thank you.
My last question was like you said that if we can represent in Pauli form, then we can do simulation. So I'm asking that is there any other way we can look into this problem?
Yeah, you can check if your algorithm has, if your state or the problem has any structure that it can be written efficiently with tensor networks. There are other simulation techniques that I have not expertise in or probably don't know about. People are developing these things. So yes, this is a research problem that I can't answer right now.
Okay,
Sorry.
thank you, madam.
Yeah.
Okay,